Hello and welcome back, AP Psych. We're getting started with our final video from Unit 1. This video is going to be touching on statistics. In our quest to find out how psychologists ask and answer questions, statistics is a huge portion of that. So if you are in AP Stats or statistics class in general, you'll have a head start on this. If you don't consider yourself to be math inclined, that's okay. The statistics that we are expected to know in AP Psychology are not as difficult or in depth, so that's nice, but they are just as important when it comes to proving our research and providing data for psychological endeavors. So let's get started. So when we talk about statistical reasoning, why do we use statistics in psychology? Well, we need to have that data from our experiments, from our research that we can analyze, because it allows us to dig a little bit deeper into information so we can see correlations, we can see trends, we can see cause and effect. And those things are super important, especially when we're trying to make psychology as scientific as possible. So below here we have some census data from the most recent census in Colorado. And you can see that statistics is useful from a basic standpoint of understanding further the demographics of Colorado, and we could make some inferences from this. We could make some generalizations from this about the people who live in Colorado. We could gain information from it and further kind of investigate based on those takeaways. So it's something interesting, and statistics is definitely a necessary component of digging deeper into research and experiments. When we're describing our data, meaningful description of data is important because misrepresentations can lead to incorrect conclusions, right? So we have to be careful, just like in history class when you're analyzing sources of information. You also need to be careful when you're analyzing sources of data and representations of data, because they can be used for people's certain biases or their certain perspectives. For example, when we look at this piece of data and these statistics here, they are the same statistics, just represented differently. We have a brand of truck and the percentage of those trucks still functioning after 10 years. When it's presented on a 100-point scale, it looks very similar, right? You think, okay, most of these trucks perform about the same, a little bit of difference, a little bit of variation, but overall, they seem to be pretty reliable across the board. But if you are our brand and your goal is to make your truck brand look significantly improved over the competition, you might only present it on a 5 percentage point scale. And that makes things look drastically different, right? Even though there is only about a 3% difference in cars or trucks still functioning after 10 years, the way that this data is represented makes it look drastically different. So we must be careful when we're describing our data or analyzing data, that we're paying attention to the way it is being represented. Just like when we talked about surveys and how we must be careful about the way surveys are worded, and that might lead to misinterpretation. So when we talk about statistics, there are a few things that we call measures of central tendency that we're concerned with in AP Stats. These are things you've probably heard of from math class, but as reminders, there's 3 major measures of central tendency. We have the mean, which is the average of a set of scores in a distribution. We get this average by adding all the scores together, dividing by their number, right? Basic average, fancy term, mean, right? We also have the median, the middle score in a rank ordered distribution, right? So if we have 15 numbers, the middle score, whichever score falls directly in the middle, is our middle number. If we have 20 numbers, the 10th number is our middle number. That's the median. Our mode is the most frequently occurring score in a distribution. So if we had 15 numbers and the number 5 occurs 7 times, and it's the most often occurring number, 5 would be our mode, right? Most often occurring. So those are our measures of central tendency that we're going to pay attention to, especially when we are looking at data sets and describing the statistics from certain research or experiments. Other things to keep in mind, other measures of variation We have something called the range, which is the difference between the highest and lowest scores in a distribution. The range is very effective and useful when we begin to look for and try to understand the standard deviation within a data set. Okay? Standard deviation is the average difference between each score and the mean. Okay? So the larger the range, the larger our standard deviation will be, because there is more difference between each score and the mean. Okay? So an example down here. We have two distributions, okay? The blue and the red. This line here on a normal curve will have all three measures of central tendency will be the same. The mean, the median, and the mode will all fall exactly in the middle here. Okay? So the red represents a small standard deviation because the scores are more bunched together. And you can tell that by the sharp, tall curve, right? Our scores here are closer together. They're closer to the mean. So our standard deviation is much smaller. Our average difference between each score is much smaller. If you look at the blue, there's a large set of scores or distribution of scores. Our range is large. So that means our scores are more spread out, further away from the mean. So we will have a larger standard deviation. The average difference between each score is larger, and the average distance from the mean to each score is larger. So our standard deviation will be larger. Okay. So let's talk about standard deviation a little bit more in depth. As opposed to those of you who are maybe in AP Stats or Statistics, in AP Psych, you will not be asked to calculate standard deviation, which should be, okay, that can be a little complicated sometimes. It takes multiple steps. We don't have to do that. But you must be able to apply what you know of the concept. And that's kind of where what we just talked about comes into play when we talk about range, mean, median, mode, the descriptive statistics that we use to describe a data set. Those are important when we talk about standard deviation. For example, which of the following sets of data has the greatest standard deviation? Okay, think about what I just talked about. A range is a perfect way to tell the size of the standard deviation. The larger the range, the larger the standard deviation. The smaller the range, the smaller the standard deviation. Okay, so if you look at these three and you analyze them a little bit, which one would have the greatest standard deviation? Well, the range here is 1 to 30. Okay, the range here, 5 to 18, smaller than 1 to 30. How about down here? 30 to 35, smallest one of all. So I'm hoping you're realizing that 1, 5, 7, and 30 would have the highest, or the greatest standard deviation, because by estimating, let me move this, the standard deviation, we looked at the spread or the range of the numbers. Okay. One other thing you could do, you could find the mean and compare each number to it. Okay. If you wanted to go the longer route, just to be sure, you could add up all of these numbers, and then divide by 4 to find the average and see how far each number was from it. Okay. And the set of numbers that have the most numbers further from that average would have the largest standard deviation. Okay, so let me go back to our standard deviation definition just to remind you. It's the average difference between each score and the mean. Okay, so it's how far scores are spread out away from our central point. The further they are spread out, the larger the standard deviation will be. Okay. So most scores will fall on something called a normal curve or a normal distribution. A distribution of scores that produces a bell-shaped symmetrical curve. This is what we call a normal curve. You're going to see a ton of these in AP Psych. Okay. In this normal curve, I talked about this a second ago. The mean, the median, and the mode, those three measures of central tendency that we use for descriptive statistics, they will all fall at the exact same point. Boom, right here in the middle. Okay? So things to know about a normal distribution. When all three of those numbers fall exactly in the middle, then you'll have 50% of your results to the left in the negative, below the average, and 50% of your results above. Okay? So a couple things you're going to want to do. You're going to want to memorize these percentages. Okay? And you'll notice they are the exact same on each side because 50% of your results are here and 50 are over here. So one standard deviation from the mean in a normal curve is 34.1%. Right? Two standard deviations to the positive side, you're going to add these two together, right? If you're talking 3, it goes to 2.1, and 4, it goes to 0.1. So notice I said one standard deviation to the positive side, right? To the higher side. Okay. But if I asked you what is one standard deviation total from the mean, I didn't specify positive or negative. So that would mean both one standard deviation to the positive side and to the negative side, which leads you to 68% of your results fall one standard deviation from the mean. Okay. So we'll look at an example here in a second with IQ to kind of further differentiate this. But what that means is in a experiment or research with a normal curve, most of your results fall one standard deviation within one standard deviation of the mean, right? That's where most people are, okay? As you get further out, the less and less of your population is represented in those areas, okay? The further you get from the middle or from the mean. All right, let's look at an example. So a classic normal distribution example is IQ scores. Okay? The average IQ score in America is 100. Okay? Most people fall within one standard deviation of the average. So they're in here on this side or here, 68%, right? That means most people are somewhere between 85 IQ and 115. Okay? IQ extremes are above 130 and below 70. So that's when you're getting into two standard deviations from the mean, is when 130 starts and 70 starts. That's when you get into your kind of like your outliers or your extremes. Okay. So just as a reminder, the span of one standard deviation on either side of the mean covers approximately 68.2% of the scores in a normal distribution. Okay. So I'm going to flip back real quick, just in case you didn't get a chance. I believe this is in your notes as well, but you should be writing and taking the time to commit to memory these percentages for your standard deviation. I wouldn't be surprised if you were asked a question on the AP exam, what percentage of people fall 3 standard deviations from the mean in a normal curve, right? And you would just need to know that percentage. So that's something that we need to memorize in here and just commit to memory so that we can reference it when we need it. Okay. As we continue our talk of measures of central tendency, we're not always going to have a normal curve in our results. Okay, so that might be something called a skewed distribution. And a skewed distribution occurs when there are outliers or data points that lie at one extreme end of the curve. And they can skew our data because they pull our curve in a certain direction. Okay? Positive or negative skew is determined by where the outlier lies. Right? So if you're looking at this example, it's kind of hard to tell, but this is a curve, right? But it's not a normal curve because it's not equal on each side of the mean, median, and mode, which you'll notice those three things, which in a normal curve are the exact same number, are no longer equal. Okay, so why is this distribution skewed? Hopefully you're realizing it's because out here on the higher side, there are some serious outliers: 710, 475, 90, potentially even 70. These are major outliers that are pulling our results and our average or our mean this direction. Okay. How could you change how would it change? Excuse me. Let me move this again. If you remove the families that made 90, 470, 475, and $710,000 per year. Well, hopefully, removing those families would shift the curve back over, and our mean, median, and mode would once again meet and form a normal distribution. So here's a couple more examples. If you have a negative skew, that means we have outliers to the left of our measures of central tendency, pulling them this way. So in a negative skew, the majority of your scores are going to be above the mean because one or a few extremely low scores are causing the mean to be pulled in this direction, right? They're causing the mean to be less than the median and the mode. They're no longer equal, okay? That's a negative skew. On the opposite end, a positive skew, the majority of your scores are below the mean over here, but your mean is being pulled this way because one or a few extremely high scores cause the mean to be greater than the median and the mode. So we no longer have a normal distribution. It's a positive skew being pulled towards the right. So having analyzed this, which measure of central tendency is most impacted by the outliers? Hopefully you're realizing that the thing that's being pulled towards those outliers and being skewed the most is our mean, our average, because those extremely low numbers or those extremely high numbers impact our average the most. So when we're talking about the most reliable examples or the most reliable measures of central tendency, our mean is actually the most unreliable because it is the most impacted by outliers. You're much more safe and able to rely on the median and the mode as your most reliable measures of central tendency. Okay, so that wraps up our descriptive statistics, right? We have our measures of central tendency, we have our measures of variation, we have our normal curves, and we have our skewed distributions, okay? Those are things we use to describe our data sets. We can gain information from them, we can analyze them, and use them to look deeper into our data to provide us with more feedback. When we get back into class, we're going to be discussing the other branch of statistics, which is inferential statistics. Descriptive is just like it sounds. We're describing a data set. Inferential is also like it sounds. We're inferring from these statistics, right? It involves estimating what is happening in a sample population for the purpose of making decisions about that population's characteristics. And it's based in probability theory. So that's a lot of jargon, sounds kind of confusing. Basically, what it breaks down to is this. Inferential statistics allows us to say, if this worked for this population, we can estimate that it will work for the rest of the population, right? And that's what we're trying to do with statistics and with research and with experiments. We're trying to take an idea, a hypothesis, and see if we can generalize it to the larger population. And that's what inferential statistics allows us to do. So here's a concrete example. If you're testing a new drug, right? You're testing out a new drug. If the meds worked for the sample population and you found out, your control group and your experimental group responded differently, and we found out that the drug was actually working with that population, we can then estimate they will have the same effects on the rest of the population, and maybe we can continue those trials, right? So inferential statistics allows us to generalize and to extrapolate to the larger population. However, there is always a chance for error in whatever the findings may be. So the hypothesis and results must be tested for significance. Remember when we touched on replication a little bit ago, a few notes ago? Replication is super important when we're talking about generalizing and extrapolating our results to the larger population. You need to do these things over and over and over again to test them out to make sure they truly are what's called statistically significant. Okay? This means there is a difference observed between two sample groups, and it is probably not due to chance. The difference instead is likely due to a real difference in population. So when we get statistical significance, we can say with almost certainty that our independent variable is what caused our dependent variable, right? And we can show a causal relationship here. The relationship is statistically significant. So how do we define that? Data is significant when the likelihood of a difference being due to chance is less than 5 times out of 100. Okay, so that is represented by something we call the p-value, which is the percent due to chance. Okay, so p less than 0.05 means the percent due to chance is less than 5%, which, if you have that designation, means your results are statistically significant, and you can extrapolate to the larger population. You can generalize to the larger population. This is important because if research is statistically significant, that means you've done it, right? Your results are probably not a fluke, like we just said. They're not due to chance. Right? You can extrapolate. You can continue your test. You could potentially take this out to the larger population and help people in different ways. So we're going to talk about some of this stuff even more in class when we get into inferential statistics, re-go over it. And I'd love to answer any questions you have about standard deviation and measures of central tendency, measures of variation. I know statistics is new to a lot of people, but know that it is a very important topic, but one that anyone can grasp with a little bit of practice, and the things that we'll do in class will certainly help make that a possibility. All right. So if you have any questions, please let me know, and I hope you enjoyed. Thanks.